Okay, this section is going to go over rotational systems. So we're going to start by looking at some equivalent elements. And these rotational systems, they can all be also be referred to as torsional systems. So there are many similarities between these and the previous translational system elements. So translational mechanical systems, we can see we have our typical drawing over here on the left. A rotational system that would look equivalent would have some sort of inertia connected to a spring with a damper connected as well. And that spring can be represented by a beam in this case. So what are our equivalent terms? Well, we have our force, which is represented by F and has the units of newtons. That is now a torque, which is in the units of Newton meters. That's equivalent in these two systems. Our velocity will be the equivalent to angular velocity, omega, which is in radians per second. Our displacement or deflection or deformation, that is x or d, with the units of meters. Now we have an angular displacement, which is going to be theta. Our masses are related to inertias, which are represented by J's. Our spring constants are related to torsional spring constants, KTs. And our damping coefficients, now in the rotational world, we have torsional damping coefficients, or constants. And that is CT. So these are all our equivalent elements. And we're going to be able to use the same tools to model translational systems and rotational systems. So what are inertias? We can just use Newton's second law to get J omega dot is equal to sum of our moments about 0.0, where that J is our inertia about 0.0, and our omega is our angular velocity, omega dot is our angular acceleration. So if we were to draw out one example for an inertia, it would look something like this. It has an associated angular velocity. Another one that would have an inertia as well, about that 0.0, is a pendulum swinging back and forth. That's still, since it has some sort of mass, it'll have some sort of inertia about that 0.0, and it has an angular velocity to it. And just like with masses, an inertia has or stores kinetic energy. So Ke is 1/2 times j omega squared for a linear case. Very similar to the translational case for these rotational systems. Torsional springs are also dependent on Hooke's law. So we have our restoring torque in this case is equal to our spring constant for the torsional system KT times our net angular deflection or twist in this case. So if we draw out a spring, and this could also be represented by a beam with some elasticity in it, we have two coordinates, phi1 and phi2. Those are like our R1s and R2s from previous videos. Those are essentially the deflection at each one of those points. And our theta there, that is our net angular deflection or twist. So in these cases, we have our torsional spring, which is related to potential energy, which is 1/2 kT theta squared for the linear case. And then finally, we have our torsional dampers, which also waste energy. So our restoring torque in this case, or damping torque, is equal to our damping coefficient times our relative angular velocity. So if we were to draw out what a torsional damper would look like, we can have it look something like this, where we have phi1 and phi2, which are our positions, or our angles for each one sides of those beams. Our damping torque in this case is going to be CT times the rate of change of those guys with the difference between those two positions or angles. And again, it's all about that relative angular velocity, just like it was about relative velocity with dampers. And that is going to cover up rotational systems.